Today's kind of proof is going to be proof by induction, and it's a little bit strange. What I really recommend is you watch this video and then you have a look at the site that I've listed here, and you also might find it useful looking at YouTube for other videos for different ways of explaining this. It can be quite challenging for some students, and it's a little bit of a strange proof, but it follows a very straightforward formula, but the application of that formula can be tricky. So I'll show you what I mean. What I want you to do is to pause this video for a moment, and I want you as quickly as you can to add up the numbers 1 to 100. Have you paused it? Have you had a go? Well, hope you have. Here is a quick way to do it. So I'm just going to write out the numbers 1 to 100. Just joking, I can't be bothered writing all the numbers. So what we can do is write 1 plus 2 plus 3 plus ... represents all of the numbers from 4 to 97, then plus 98 plus 99 plus 100. Well, Gauss, the story goes, was in class and his teacher wanted to basically, give him a task to do, make him busy because he was very intelligent and possibly a troublemaker. I don't know if that's actually the story, but let's just say it is. Gauss was able to figure out a really efficient method of being able to figure out the sum of 1 to 100, in mere moments. What he did was he wrote out the same list underneath the first one, basically, but in reverse. So hopefully you can see that's exactly the same thing. Then he noticed an interesting pattern. If you add these two terms together, 1 and 100, you got 101. And if he added 2 and 99 together, he got 101. And he added 3 and 98 together, was 101. And he found each term, when he wrote out the list frontwards and backwards, nicely paired together to give 101. So if he added the purple list here to the blue list, the first list to the second list, for anyone who's colourblind, he found he got 101 for each pair. Now I want you to think, how many 101s did he get? Well, hopefully you realise he would have had 100 101s. So I'm going to put an equal sign but leave a little gap underneath, and you'll see why in a second. So he got 101 times 100, so 100 lots of 101. The problem is that calculation won't give him the sum from 1 to 100. It gives him 2 lots of the sum of 1 to 100 because he's adding that first list to the second list. So if we take that first list and divide everything by 2, that line above and divide everything by 2, that will give us how to find the sum from 1 to 100. So hopefully you can see 101 times 100 is 10100, divide it by 2, and we get 5,050. Because half of 100,000, half of 100. I'm going to show you why this works a little bit later on. And the rule that dictates this will be n on n plus 1 divided by 2. And I'll show you that a little bit later on, so I want that sort of in your brain for a little bit later. But what we're doing with proof by induction is we want to find rules without needing to show that it works for an inordinate number of numbers, or even you might find a crazy number of numbers, an infinite number of numbers. That's something that we wouldn't be able to do even if we computed for the remainder of our lifetimes, and the next generation computed for their lifetimes, and so on and so on. Proof by induction is a pretty nice way where I like to imagine it as a stack of dominoes. And I imagine, well, if I can deal with the first domino and I just make sure that it knocks the next domino and I've set up all my dominoes correctly, rather than me having to individually knock over each domino, I could just knock over the first one, making sure I've set it up correctly, and all of them are going to fall over. I was in a humorous mood when I wrote this. Proof by induction is a pretty sick method that allows you to check for every single number of something in less than an infinite amount of time, which is pretty awesome. So the formal way this recipe is sort of set up. Step 1, you start with the statement you wish to prove. So there's 4 steps here. Step 1, that's going to be a question that I give you. So as I joked about in class, 25% of these steps have been done for you, i.e., step 1 is done. It's the question that you're asked to prove. Number 2, you want to show that this statement is true for n equals 1. You'll notice there's a little star here. Occasionally we don't start at n equals 1. We'll start at n equals 2 perhaps, or 3 or 4. Depends on the question. For example, if you were told n is an even number, you would start at n equals 2, the smallest even. Or if n was a prime, n equals 2 as well. For a lot of it we start at 1, but you'll see. Step 3. Show if the statement is true for some magical number n equals k. And I talked in class, k is a magical number that exists on the planet, and I tried to draw like a wizard's, wizard's hat. Didn't have much more success in class, but k is this wonderful magical number that we know definitely works. And we're saying if the statement is true for n equals k, we can't just say for n, because n represents all of the various numbers that could exist in this particular problem. K is one specific magical number that we know works. So if k works, then our proof recipe says if k works, show that it also works for n equals k plus 1. So that would be the next consecutive number next to k. So it's saying if k works, show that k plus 1 also works. Then you want to say, well, if you've shown it's true for n equals 1, and then you showed it was true for n equals k, so k could be 1, then it had to work for k plus 1. So that means it must be true for n equals 2. And if it's true for n equals 2, then it needs to be true for n, equals 2 plus 1 equals 3. So it's like we're setting up our first domino, we're making sure all our dominoes are set up correctly, and then we're just knocking over the first one. Some people struggle with that recipe, so I sort of put it in easier terms. It says, start with what you want to prove. Again, 25% of the steps are done for us. Show that it works for one number. Often we start with n equals 1. Imagine in this universe there's a magical number k that definitely works. We don't know what it is. It's shy. If k works, then k plus 1 should also work. As I said in class, we need to sort of massage or manipulate the equation to look a certain way. And you'll understand better what I mean when you've seen a few examples. And then, like number 4 we saw before, once you've shown it works for n equals 1, the induction step shows that it worked for n equals 2, so it's true for 3, and we've knocked over all of our dominoes. Okay, it's a little bit weird, but let's have a look at this first example. This should hopefully remind you of what we started the lesson with. We want to prove that 1 plus 2 plus 3 going all the way up to some number n equals that last number n times n plus 1, so the next consecutive number, divided by 2. We cannot start by saying left-hand side, which would be this side, equals right-hand side. We're imagining that there's a question mark in front of that equals. We need to start with the left-hand side and show that the right-hand side follows. That's going to be a bit later on, but I just need you to keep that in mind. So, there were 4 steps that we used to solve this. Number 1, start with what you want to prove. Done. So we want to show that if we add up all the integers starting from 1 going to n, we get, what we talked about before. Number 2, we need to show it's true for n equals 1. So show true for n equals 1. We're probably going to need both sides of our area here, so I'm just going to rule a line. Okay, showing it's true for n equals 1, you must do it this way. Some textbooks, will give you a pass, and some teachers will, but I won't. Normally I wouldn't write left-hand side, right-hand side already above each other. Oh, that's my doorbell. 1 second. Okay, where were we? We were showing this was true for n equals 1. In order to do this, we need to substitute 1 into the left-hand side, which we abbreviate to LHS, and into the right-hand side. And hopefully you recall this from, pseudo-proofs that you've done in the past. You want the left-hand side to equal the right-hand side for this to be true. So the left-hand side, what that left-hand side is saying is, start with the number 1, and you're going to keep adding on the next integer until you get to your last number. Well, if we're just saying n equals 1, that means our list, we start with 1. We're not going to do plus 2 because we've already reached 1. So we just say left-hand side equals 1. It's just saying start with that first integer, keep adding till you get to whatever you wanted n to equal. If n's already equal to 1, we just have 1 on the list. Now we're going to substitute it into the right-hand side. So we're subbing n equals 1 into this here. So we're going to do 1 in brackets 1 plus 1 over 2. 1 plus 1 is 2. 2 divided by 2, and we've just got that times 1 there. We're also going to get 1. So left-hand side equals right-hand side, therefore true for n equals 1. People are asking me in class whether they do need to write these little sentences here, and I said, no, but. And the but is, it actually kind of helps writing that because it's signaling to you what you're doing, but also signaling to your examiner what you're doing. So it is a good idea. You might want to write it, in shorthand or in a more efficient way, but you might even there say left-hand side equals right-hand side, therefore true. Like, that's okay, but really think this is about communicating your process. So try not to, be dodgy and stingy on your working out. Okay, that was step 2. Step 3 is a little bit odd. Step 3 is, well, we're going to assume it's true for n equals k. So k is a magical number where we know if we substitute it into this formula above, plus ... plus instead of n we're going to have k, we know, so there's no equal sign, there's no question mark above this equal sign, we know for sure that it equals this on 2. That we can say we know that for sure, and I'm going to call that our start equation. So we know for sure that if we do 1 plus 2 plus 3 plus blah, 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 plus k, it equals k, open bracket, k plus 1, all over 2. For example, we knew 100 worked because when we did 100 in the example above, it worked. We did, 101 times 100, that's like our n plus 1 times n over 2. So you can imagine if it helps that that's like 100, but not necessarily 100 itself. Maybe it just works for another number, but I'm sort of getting off track. The whole point is we're going to assume that this equation is true. And this is the exciting step. We need to now show that it works for n equals k plus 1. Now show, is this step 4? Was this a separate step? No, it was part of step 3. Step 3 is the long step. Step 4 is our just finishing off step. So now, show it's true. We need to show it's true for n equals k plus 1. Okay, so something that I sort of told people is we're starting with the left-hand side and we want to end up with the right-hand side. So for the right-hand side, I'm just going to do this on the side. If we substituted n equals k plus 1, what we'd get is, so I'm just going to write this equation so you can visualize what we're doing on 2. N is going to become k plus 1, so we need to put brackets around that k plus 1 now. But we've also got to put it into this n, so we've got k plus 1, but we've still got this plus 1 at the end, all over 2. So k plus 1, k plus 2, all over 2. So we're hoping in starting with the left-hand side of this equation, so starting with this, but substituting in n equals k plus 1, we can eventually get to this. Some people like to have left-hand side, right-hand side, and then show that they equal each other, and I demonstrated that in class, but you don't have to do it that way. You can just say, substitute k plus 1 into it on the side of your page, if you like. Okay, so let's actually give this a go. So we're going to substitute k plus 1 into here. So we're going to have 1 plus 2 plus 3 ... plus, instead of n, we've now got k plus 1. Notice we're not writing equals this because it's like there's an imaginary question mark in front of there. We don't know it equals that yet. So we can't just let that equal it. Now, this is the, manipulating or massaging kind of part of what we're doing. We're really, really hoping that we can find this in what we've just done here. Because if we found 1 plus 2 plus 3 plus ... going all the way up to k, we would be able to say, I know what that's equal to. So what you can do is sort of go back a step. So, for example, I could write 1 plus 2 plus 3. I can write another term here, plus 4 plus ... That's just putting in another term. That 4 was within the ... before. It doesn't hurt writing that in. We don't have to though, but I'm just showing you that we can. So if we can put another term in there, we could also put the term before in here. The term before k plus 1, well, you know, the term before 3 was 3 minus 1 was 2. So the term before k plus 1, take away 1, must have been k. So if we've got k, then we can write k plus 1. Now the reason we did that is because we've seen this before. That is this here. Now you might say, why couldn't we just use this k here and take that? Well, unfortunately, k plus 1 is an entire number. You can't separate that out. K plus 1 is like the number 100. You can't be like, oh, I'm just going to steal 99 away from 100, you know, and make it just 1. So k plus 1 is an entire number. So that formula that we previously found, we have now, oops, I meant that for it to be a highlighter. 1 second. We've found that within our k plus 1 equation. So that means we can replace that 1 plus 2 plus 3 going all the way up to k with this, because we said this is true. There's no question mark above this equals sign. So we can now write, instead of 1 plus 2 plus k, 1 plus 2 plus 3 going all the way up to k, we can write k plus 1 over 2. Now we've still got that k plus 1 here, so we're just going to write that in. So the real trick of this, the thing we had to think about, is how can we replace something in our k plus 1 equation with something from k that we already know? And if it gets rid of a whole lot of ... stuff, all the better. Now we've got this, and in the back of our mind, we're thinking, I really hope once I do some algebra to this, I'm going to get something that looks like this. At the moment, we have, you know, 2 separate chunks to this equation here. But here I notice everything has a common denominator. So let's look at what we've got, and let's give it a common denominator. So if we had a common denominator of 2, we're just going to have k plus 1 on top. And it's like we've multiplied this, because it's technically over 1, times 2 times 2. But to multiply it by 2, we need to put that in brackets. So that means we've got plus 2k plus 1. Hopefully you remember from maybe year 9 or year 10 maths, when you've got a common factor in a bracket here, you can take out that common factor k plus 1, and then we scoop up these things and pop them inside of a bracket too. We've still got it all over 2. Perfect. That's exactly what we were hoping for. So if you want, you could have labelled this as the left-hand side, because we started with the left-hand side here and not multiplied, substituted in k plus 1. And then we substituted it into the right-hand side. So if you want to put that working out in, some people really like having that in there because it helps them visualize it. And then they say, well, left-hand side equals right-hand side. Therefore true for n equals k plus 1. In our recipe above, we said, let's show it works for n equals 1. Then we'll assume it works for n equals k. Does it work for n equals k plus 1? Well, here it did. And once we've concluded it works for n equals k plus 1, this is the exciting step. Therefore, true for all n. Now, just to be clear, here it appears n was a natural number. So we need to specify, it's not just all n like all the real numbers. We want it to be an element of the natural numbers. Or you could have said n is an element of the positive integers. that's also okay, because the positive integers is just the natural numbers. I'd accept that. So that was step 4, technically. Step 3, does it work? No, assume it works for n equals k. Does it work for n equals k plus 1? Step 4, oh, it did work for n equals k plus 1? Well, then it must work for all of n. We've knocked over all of our dominoes. We're going to have a go at the next one now. Prove that n squared minus n is true for all integers n is greater than or equal to 1. So it looks like we've got n is a natural number again, positive integers. I want you to pause and have a go at the first step. Actually, the first step's been done for us. Start with what you want to prove. Have a go at the second step. I want you to show that this is true for n equals 1. If you're not sure, you're welcome to just watch and see where we go with it. Okay, so you might have paused and you're waiting to see how we go, or you're just working along with me. So we need to show that n squared minus n is even. So we'd better substitute n equals 1 because that's the first relevant number. N was greater than or equal to 1. If n was just greater than 1, but it was an integer, we'd have to start in this example with n equals 2. But it's greater than or equal to. So show it works for n equals 1. Okay. So this one is not really a left-hand side, right-hand side. We're going to substitute in 1, and let's see if we get an even number. We're hoping it's even. So if we put in 1 squared minus 1, because n is equal to 1, that equals 0. And just for future reference, 0 is even. It's even because either side of it is an odd number, 1 and negative 1. When we're talking just about integers, to be clear. So that's even. So therefore, true for n equals 1. So that's often the easiest step. Now we get into the harder stuff. 3. We're going to assume it's true for that beautiful number n equals k. So that means we can write with all confidence in the world, k squared minus k is even. No question mark over the is. This is true. This is the most important thing in our lives at this moment. If it's true for n equals k, we need to show it's true. So show true for n equals k plus 1. So we need to substitute n equals k plus 1 into here. So that means instead of n squared, we'll have k plus 1 squared. Minus n becomes minus k plus 1. For the love of mathematics, please put brackets here. Please put brackets there. So let's expand this out. If we expand this first one out, we'll get k squared plus 2k plus 1. And then we're going to have a negative that we need to distribute here, minus k minus 1. Now, this is the massaging step. We're thinking, is it possible for us to find this k squared minus k in what we've got here? Hopefully you can see we've got a k squared here, and we've got a minus k here. So let's put those two together. So that means we've got k squared minus k. I notice we've got a plus 1 minus 1, so we'll just get rid of that. And then plus 2k. So hopefully that is exciting. And if not, I'll explain why it is. We previously said that this was even. Because we said, yep, it works for k, so that means k squared minus k is even. That's what we said in this step here. And as we've talked about previously, something times 2 is also even. So 2k has got to be even. And we've also previously shown that an even plus an even gives you an even. So we're about to fall off the page. Let's go up here. Might go a bit smaller. So that means, therefore, it's true for n equals k plus 1. And if it's true for n equals k plus 1, remember we said step 4, that means, therefore, it's true for all n is an element of the natural numbers. So we had to do a little bit of mathematical trickery here. We didn't do anything mathematically illegal, but we had to make it work so that we had that k squared minus k that we could replace that with. We knew information about k squared minus k. We knew it was even. And then very, very, well, it's not lucky because it's proof. We've done all the steps that are proper for this. We then found, well, we had another term, and that was plus 2k, and that's even too. And we know an even plus an even gives us an even. So proof by induction can be a little bit strange, but it works. Trust me, it works. I want you to have a go at some of the next ones. I am going to not do a voice recording because I realize this is a very long video. I am just going to do the working out, and I'll speed it up a little bit, but you can pause it whenever you need. Okay, for this bit here, it's a little bit trickier, so I thought I would come back and explain what we're doing. And I wish I'd done my ruler straight from the get-go because I will need the other side. We've currently got 7 to the power of k plus 1 plus 2. We very much need to do a bit of mathematical manipulation here to get this, because we want to be able to find 7k plus 2 inside of here. We're so close, but we've got 7k plus 1. We've got this 7 to the power of k plus 1 here. So we can add or subtract things onto the end of this to make this work. And I'm thinking, like I said in the previous example, actually, I don't know whether I've done this kind of example with you yet. I just what do you think? Is it true if I did plus, I don't know, let's pick a random number, plus 10 minus 10 here? Have I fundamentally changed this? Hopefully you're thinking no, because plus 10 minus 10 will give us, 0. So that doesn't affect what we're doing here. So you're allowed to add or subtract something on the end. What I'm thinking is, I want to get 7k plus 2 somewhere. That 7k here could be written as 7k, sorry, I keep saying 7k, I mean 7 to the power of k. 7 to the power of k times 7 to the power of 1, which we'll just write as times 7. So I'm thinking, could I take out 7 as a common factor here, so I could get 7k plus 2 in the brackets? Well, if I had 7k plus 2 in the brackets, 7 times 2 would be 14. But we currently have a plus 2 here. So I'm wondering, how is it that we could have 14? Well, if we added 12 and took away 12, we could get 14 here, which we could then have 7, and then I'm just going at 7 times 7k plus 7 times 2 is equal to 14 minus 12. And then here we've taken out 7 as a common factor, and in the brackets had 7k plus 2, because remember, our desperate desire is to have that 7k plus 2 that we previously said we know information about. We know that 7k plus 2 is a multiple of 3. So adding and subtracting 12 is the trick that we needed here. So that 2 plus 12 became the 14. We had 7 times 2 is 14. We took out 7. So we've got minus 12 at the end here. This is a trickier one, so I want you to really think about this one and really examine it and really digest it, because it's a little bit odd. So we've nearly finished. This here is a multiple of 3. Because we previously said, yep, 7 to the power of k plus 2 is multiple of 3. And 7 times the multiple of 3 is still going to be a multiple of 3. Now 12 is also a multiple of 3. 4 times 3 is 12. If we have two things that are a multiple of 3, then you could imagine we could take out a common factor of 3 and write everything else inside of there. So that means the whole number is a multiple of 3. Therefore, whole number, mult of 3. So that means it's true, therefore true, for n equals k plus 1. And remember step 4, therefore true for all n is an element of n. Okay, have a watch of this one and see how you go. Okay, so hopefully that proof was kind of nice. It did rely on that trick where we were writing out this long list that we wrote one term beforehand so that we could substitute in this k squared here. If you have any questions about this, make sure you check out the website that I showed at the start. Please send me an email or make a time. Well done, everyone.